Hello there, Mr. Sutton here, bringing you the Algebra 2 8-1 lesson on sample space and probability. This will be a two-parter. In part 1, we're going to be learning how to list possible outcomes in a sample space and also figuring out theoretical probability. And then in part 2, we'll turn our attention to geometric and experimental probability. So to start off this lesson, here's a question for you. What is the probability of a coin flip coming up heads after 99 out of the first 100 flips come up heads? Pause the video and let's see what you think. Alright, so you might have answered that the probability of a coin flip is going to be 1/2 chance of getting heads. You might have also answered that it's 99 out of 100. And those are actually both correct depending on the type of probability that we're talking about. It turns out that there's theoretical and experimental probability, and we'll get into all of that as this lesson unfolds. But let's first start with a general definition of probability, which is the likelihood that an event will happen on a scale from 0 to 1. So here's a little scale to show you this. 0 would be impossible, 1 would be certain, and then we have everything kind of in between. And it says unlikely 1/4. It doesn't mean it's exactly 1/4. It's just kind of a general ballpark of what we call these things. Now you might notice here that we can express probability as a fraction in the top here, but also as a decimal or a percent. These are all acceptable ways of presenting it. Typically, if we're going to express it as a fraction, it's a reduced fraction. And kind of as a general rule, if it's a crazy fraction that's not a nice neat one like these, we typically tend to go with a decimal or a percent. So one other thing that we'll define here is something called the sample space. Now the sample space is all of the possible outcomes of an experiment. For example, with this coin flip, our sample space was heads and tails. And there's a notation that we're going to be using throughout this lesson. It's this P of A sort of notation, kind of looks like a function. This just means the probability of event A happening. I think you'll agree it's a much more concise way of expressing that. So although we're kind of early in the conversation about probability, one thing you might have sensed is that this idea of sample space, the total number of possible outcomes, is kind of important. If you want to know the probability, this is one piece of information that you need to have. So we'll start by getting a little practice finding a sample space. So let's say that you flip a coin and roll a 6-sided die. And let's say that these are a fair coin and a fair die. No cheating here. We want to know how many possible outcomes are in the sample space for these two events, and then list those possible outcomes. So I think we could pretty quickly figure out the sample space for one of them. I mean, a coin, there's two things you could have happen, and I'll let you guess how many happen on when you roll this die. But if you have two events happening at once and you're combining them, for multiple events, the overall sample space is going to be the product of the individual sample spaces. So let's see if you can implement that. Pause the video and see if you can answer the question. Alright, so let's break these down individually first and then we'll put them back together. So for the coin outcomes, we know that there's two of those, heads and tails. And then for the dice roll outcomes, there's going to be 6 of those because it's a 6-sided die. And we have the numbers 1, 2, 3, 4, 5, and 6 for those. Since there's 2 coin outcomes and 6 die outcomes, that means the overall sample space is going to be 2 times 6, or 12. So 12 different possible outcomes, a combination of a coin flip and a die roll. So just listing those out, we have the possibility first off that we rolled heads and one of these numbers, like 1. So we have heads and a 1, heads 2, and then I'll just abbreviate these, H3, H4, H5, and H6. And then we could flip tails and get all of these numbers as well. So T1, T2, T3, T4, T5, and T6. So it's kind of tedious writing out some of these sample spaces, and some of them can get quite large. The key on this is just to be systematic. Now that we've talked a little bit about sample space, let's dig a bit deeper into this idea of probability. The first type of probability we're going to spend some time on is called theoretical probability. Theoretical probability, like all probability, is a ratio, it's a fraction, and this is going to be the number of favorable outcomes to your experiment divided by the total number of possible outcomes. So for example, in that coin flip, there was one favorable outcome, you were trying to get heads, and two possible outcomes, heads or tails. So the theoretical probability of heads, even after 99 out of the first 100 flips come up heads, is still going to be 1/2. With theoretical probability, it's all about what could happen, and it has nothing to do with what has already happened. Although this is kind of suspicious, that wouldn't be the theoretical probability using the 99 and the 100. Now, this does kind of highlight something important about theoretical probability. We are assuming that all of our outcomes are equally likely. If we don't have an even chance of heads versus tails, then this 1/2 no longer applies. In general, if the problem does not specify the type of probability, then we're going to assume it is theoretical probability. So now that we understand a little bit about theoretical probability, let's take it for a test drive. Let's say we have a student taking a quiz and randomly guessing the answers to 4 true-false questions. Not like anyone would ever do that. We want to know the probability of the student guessing exactly 2 correct answers. Now there's a few ways of doing this problem, but one of them is kind of the brute force approach, which is to write out all of the possibilities and then figure out the theoretical probability from that. If you're going to use that approach, which is kind of what I'm showing at this point, it's not a bad idea to draw a little table. So in this table, you have maybe the number of correct answers, different ways of getting that number of correct answers, and then the total number of ways of getting those correct answers. So with this in mind, pause the video and see if you can figure out this theoretical probability. All right, now if we have 0 correct answers, that means that our outcome, there's only one way to get that. That's if you got incorrect on all 4. And there's only one way that that's going to happen. Getting 1 correct answer, you could have gotten the first answer correct, or the second, or the third, or the fourth. So there's 4 different ways of having 1 correct answer. 2 correct answers, well, you could have had the first 2 correct, or the first and the third, first and the fourth. You could have had the second and the third, the second and the fourth, and then you could have had the last 2 correct. So there's a total of 6 different ways of getting that. For 3 correct, that's kind of like 1 correct. This is actually kind of like having 1 incorrect. So your last one could have been incorrect, or maybe the third one, or the second one, or the first one. So 4 different ways of getting that. And we're seeing kind of there's this symmetry maybe developing here. And then finally, there's only one way to get all 4 of them correct, and that is if all 4 of them are correct. So that's 1 there. So then the probability of getting exactly 2 correct is all about this 2 row here. There's 6 ways that you could do that, and total number of possibilities would be the sum of all of these. So 6 plus, I guess this is 5 and another 5 over here, so that's a total of 16. And then if we want, we could reduce that to 3 over 8. For this next example, we have 2 6-sided dice being rolled, and since there's a sample space of 6 for each of those, 6 times 6 gives us 36 total possible outcomes for 2 of them. They want us to find the probability that the sum of the 2 numbers is not 6. So taking a look at all these possibilities, we see some of these that add up to 6 and a whole bunch that don't. So at this point I'm going to introduce a new concept called a complement. The complement of A is basically the probability of not A happening, or the probability of A not happening. And there's a fancy notation for it. You just take whatever the original event was and stick a line over it, and this means the complement, the probability of that not happening. Since there's a 100% chance of something happening or not happening, we can find this complement by just doing 1 minus the probability of it actually happening. So for example, if there is a 30% chance of rain, then the complement of that would be 100 minus 30, or 70% chance of not getting rain. Now, the reason I bring this up, other than the fact that you may sometimes see this on various problems, is that sometimes it is much easier to find the complement of an event and then subtract that from 1. So, for example here, you could go about finding the probability that the sum is not 6, but maybe it would be easier to find the probability that the sum is 6 and then subtracting that. So you do you. Pause the video and figure this out any way you want. So I'm going to go with the complement approach. The probability that the sum is 6 is going to be much easier to find. Now, taking a look at these numbers, just going by row or column by column here, 1 and 5 adds up to 6. That's our first one. And if you look at the diagonals here, the diagonals, the way this is set up, have the same sum. So we have 2 plus 4, 3 plus 3, 4 plus 2, and 5 plus 1. So there's a total of 1, 2, 3, 4, 5 different possibilities where the sum is going to be 6. So 5 out of 36. Now, so this is the complement of what we're actually looking for right here. So if we want to find the probability of not 6, we just have to take the probability of 6 and subtract that from 1. So not 6 is just going to be 1 minus 5 over 36, which if we get a common denominator, that would be 36 over 36 minus 5 over 36. That's just going to be 31 over 36. So our next set of problems is going to require a little bit of a background knowledge of a standard deck of cards. I mean, there's probability problems where we're talking about marbles or spinners and they kind of spell everything out. But with a standard deck of cards, they just kind of assume that you know what is in a standard deck of cards. So if you don't, this slide is for you. A standard deck has 52 cards in it. That's 2 colors, 26 cards in each color, red and black. And each color has 2 suits. So that's a total of 4 suits in the whole deck. And you can think of these suits as kind of like families. So the 4 suits, there's 2 black suits. Those are the clubs and the spades. And there's 2 red suits. That would be the hearts and also the diamonds. Each of these suits or families has 13 cards within it. And here's just an example using the diamonds here. So we've got the cards 2 through 10, and the number of dots tells you the number that it is. We also have a jack, a queen, and a king, and we also have this weird one, the ace. The ace actually counts as a 1 numerically, but in a lot of games it's the best card. We also have these 3 cards that have human faces on them, or sort of human faces. Those are actually called face cards, the jack, the queen, and the king. That's what we're talking about with face cards. And because there's 4 different suits, that means that there's actually 4 of each of these different numbers. So there's 4 kings, 4 queens, 4 jacks, 1 of each suit. Same with all these other numbers. So now that we've seen what's in a standard 52 card deck, pause the video and see if you can find the probability of picking the following 3 types of cards. Alright, let's go through them one at a time. So first off, they want a diamond face card. So we know the total possibilities is 52. There's 52 cards in the deck. Now, of those, how many are diamond face cards? Well, there's 13 diamond cards, 13 of each suit. 3 of those are face cards, the jack, the king, and the queen of diamonds. So this would be 3 out of 52. And then for the black 3, there's 4 3s total in the deck, 1 of each suit. Only 2 of those are in black suits, though, the 3 of clubs and the 3 of spades. So this is going to be 2 out of 56, which I can actually reduce to 1 out of 26. And then finally, not a king. Well, there's a lot of cards that are not kings, so it actually might be easier to figure out how many cards are kings and then subtract that from the total. So we know there's going to be 4 kings, just like any type of card in this deck. So 4 out of 52. We're going to subtract that from 1. So basically subtracting that from 52 over 52, which gives us 48 over 52. And if I want, I can reduce that by 4s to be 12 over 13. So this concludes part 1 of our lesson on sample space and probability. Join us After you do a few practice problems, in part 2, we're going to be taking a look at experimental and geometric probability. Welcome back to part 2 of our lesson. We're going to kick this one off by throwing a dart at this board right here. So they're telling us that the dart is equally likely to hit any of the points inside the square board. So we're not even considering the possibility that you're going to completely miss this square board. You're going to hit something. We're guaranteed that. They're asking, are you more likely to get the 10-point bullseye or this 0-point sort of one of these four corner pieces? So what kind of probability is this? Well, since we're equally likely to hit any of the points inside the board, we can think of this as a theoretical probability, but it's a little bit tricky because if we're asking, what are the favorable outcomes, versus the total possible outcomes, that's kind of hard to tell. I mean, there's sort of an infinite number of spots inside this bullseye even that we could hit. So another way to think about this that makes it a little easier is the concept of geometric probability, where instead of favorable outcomes, we talk about a desired area. And by the way, this doesn't just apply to areas, it could also apply to lengths or volumes, but area is kind of the most common case we see. So let's think of this as a desired area for the favorable outcomes. For the total possible outcomes, we're just talking about the total area that we could hit. So with that in mind, we're going to try to figure out the probability of getting in the 10 area versus the 0, and then compare them. We'll actually do the 10s together. So first, let's look at the desired area, this little circle in here. What is the area of a circle? Well, it's pi times the radius squared. The radius, according to this diagram, is 3, and it's 3 more for each ring that we go out here. So this is going to be pi times 3 squared, which we'll calculate in a minute. Now for the total area, that's this entire square shape here, this entire, I guess, rectangular or square area. They did say it was a square, so that's important. Now for a square area, that's just going to be one of the sides squared. Well, how long is one of these sides? All we have to go on are these 3-inch measurements here. So to go halfway through this square, it takes us 3, 6, 9 inches. So that means the total side of the square is going to be 18 inches. So we need to do 18 squared for that. And then we'll just crunch this on the calculator and see, we're going to see what decimal this comes out to. We don't need to express this as a fraction. So here I am on Desmos. Let me just create a fraction, and I can just write pi for pi. And then we've got 3 squared, that's our numerator. In the denominator, we just have 18 squared. And this comes out to about 0.087. So 8.7% chance if you had to give it a percentage. So with that in mind, pause the video and see now if you can figure out the geometric probability of hitting one of these corner pieces. All right, let's see how that worked out. So this was a little bit trickier. In order to get one of these corner pieces, we basically have to take the whole square and subtract all the circles within it. So we already know that the area of the square was 18 squared from what we did here. Now we're going to subtract this largest circle. That has a radius of 9, so this would be minus pi times 9 squared. And then the total area is still the whole square board. So plugging that into Desmos, let's just go down one, fraction, 18 squared minus, and now we've got pi times 9 squared all over 18 squared. And that's about 0.215, so 21.5%. So clearly we have a much higher chance, almost more than double chance of hitting 0 versus the 10 area. For our next problem, we have another situation where somebody is trying to aim and be accurate. In this case, we have a basketball player trying to make a free throw. And we also have some data here based on 3 games telling us how many free throws this player made and missed. And for those of you who don't really know basketball, a free throw is basically you just stand about 10 feet away from the basket and get a free shot without somebody trying to block you. So if we try to think of this from a theoretical standpoint, the sample space is, making the free throw and missing the free throw. There's two outcomes. So that would suggest theoretically this player has a 50% chance of making the free throw. But that doesn't really track with real life basketball players who typically have a much better than 50% free throw percentage. So something else is going on. It doesn't seem like there's actually an even chance of missing versus making. Now, if we look at this from a geometric probability standpoint and think of this as, the volume of this little space here versus the volume of all the places that this basketball could end up, that doesn't really make sense either, because that would be much lower than 50%. This is a tiny drop in the ocean of space in a basketball arena. So this is a situation where geometric doesn't work and there's just too many variables to figure out the theoretical end of it, where all we really have to go on is the data. In situations like this, we have something we can use called experimental probability, where we take the number of actual successes that we've already measured and divide it by the number of trials. So we still have sort of a favorable outcomes over total something, but the total something is now times that we've tried something, not really thinking about how many different ways it could end up. So a good example of experimental probability, just to draw on our coin flip that we did the beginning of the lesson with, let's say we flip that coin 100 times and 99 out of 100 it comes up heads. Theoretically, there's still a 1 in 2 chance of getting heads. The experimental probability of heads after 99 out of 100 come up heads is actually 99 out of 100. This is because experimental is based on what has happened and not what could theoretically happen. It's based on history. So with that in mind, see if you can calculate the experimental probability that our basketball player makes a free throw given these statistics about what's already happened. All right, so we're going to try to figure out number of successes and number of trials. Number of successes is just how many free throws were made over the 3 games. So 5 plus 8 plus 9, which, let's see, 13 plus 9 is 22. And the total number of trials is the total number of attempts, both made and missed. We've got 22 that were made. We have another, let's see, 3 plus 9 is 12, plus another 5 is 17. So 22 plus 17 gives us 39 total trials. So that means that the experimental probability would be 22 over 39. And if we want to convert that into a percentage, because this, fractions, this isn't really how basketball statistics are given to us. Going on to Desmos, 22 out of 39, that comes out to about 0.56, or roughly 56.4%. So it actually is pretty close to 50-50 for this particular player. And let's just see him shoot a few of these just for fun. So first one, oh, that was a brick. That didn't work out. Second shot, now that went in. And here's the third shot. Ah, well, that was disappointing. All right, on to the next problem. For this next problem, in the United States, we have a survey of 2,184 adults, over 18, and this survey finds that 1,328 of them have at least one pet. All right, and the types of pets these adults have are shown in this graph here. We want the probability, based on these statistics, that a pet-owning adult chosen at random has a dog. One of the trickiest parts of this is figuring out what type of probability is going on. On the one hand, we've got some data, so this definitely seems like an experimental sort of probability. On the other hand, given this data, where we have a randomly chosen person, so presumably we have an even chance of picking any one of the people involved in this problem. So is it theoretical or experimental? I don't really know. But it is a type of probability that we're going to give it a shot here. So pause the video based on the information that they've given us here and see if you can figure out what combination of numbers to put in a fraction to get this probability. All right, so if we're looking at this from like a number of successes or favorable outcomes sort of standpoint, the favorable outcome is that our pet-owning adult has a dog. looking at our table, because this is the only place we know about dog totals, it looks like there's 916 who said they had a dog. So clearly our numerator on this one should be 916. But now what's the denominator? What's the total number of possibilities, or the number of trials, as it were? Well, this is a little bit trickier because the whole survey was 2,184 adults. On the other hand, only 1,328 of them had pets, and they asked the probability that a pet-owning adult had a dog. Not a general, just run-of-the-mill adult, a pet-owning adult. So we actually do need to go with the 1,328 here. And just kind of running the numbers on the calculator for that, we have 916 divided by 1328, and that comes out to about let's see, 68, that'd actually be 0.690 if we round it off, or 69.0%. So those are the chances that our person actually has a dog. Now you might have been wondering, well, hold on a sec, why wouldn't we just add up all of these? Let's see what happens if we actually do add those up. So we have 916 plus 677 plus 146 plus 93. And that adds up to 1,832, which is considerably more than the 1,328 that they said had a pet. So what do you think is going on with that discrepancy? Well, these are these are the people who own at least one pet, and that's the key, at least one. So it is possible that some of these people own both a cat and a dog, and maybe even a fish and a bird. Full house of pets there. So that's it for this one. Whether you own a dog, cat, fish, or bird, maybe you should turn the video off and go spend some time with them in between doing your homework problems there. Until next time, Mr. Sutton signing off.